Hey guys, Mr. B here, and in this video we're going to be going over the chapter 11.1 notes on describing chemical reactions. Alright, so writing chemical reactions, how do you write a word equation? So understand that when we're writing chemical reactions, there's a general formula where we have names of the reactants to the left, and then we have names of the products to the right, and we have plus signs that separate everything out, and this arrow that separates out the reactant side from the product side. Okay. Now it shows here two reactants and two products. You can have any number of reactants in any number of products. You can have one reactant and two products, or two reactants and one product, or any number. Okay. But the arrow is the dividing line, and we have plus signs between every piece. In a word equation, we'd be writing the names of these things. In a chemical equation, we'd be writing chemical formulas. So here's an example of one. So we have methane plus oxygen makes carbon dioxide and water. So this would be like the gas that comes out of your stove if you have a gas stove. So it shows that methane and oxygen are reactants, carbon dioxide and water are products. Here's another example. Iron and oxygen make iron 3 oxide. So this is rust. So again, iron and oxygen are reactants. Iron 3 oxide is a product. One more. This one is hydrogen peroxide. So we'll see that there's only one reactant here, hydrogen peroxide, and then makes water and oxygen. And this should technically be a plus sign, but hydrogen peroxide actually reacts with ultraviolet light. So it reacts with sunlight, and it decomposes very quickly. That's why if you have any hydrogen peroxide in your house, it's in a dark brown bottle to protect it from sunlight. Otherwise, it'll break down into basically just water, and then it's not very helpful at that point anymore. So, all right. So obviously, word equations are kind of just a good beginning point, but that's not really what we want to do. We are looking to write out chemical equations, right? So a chemical equation is the representation of a chemical reaction. Again, we have formulas of the reactants on the left, and then we have formulas of products on the right, okay? So we can take, for example, one of these and turn this word equation into a chemical equation. Okay, so if we wanted to make this a chemical equation, we would need to write chemical formulas for this. So iron is Fe, oxygen is O, but oxygen is a Brinkelhoff. So basically, it is one of the 7 elements that when it's by itself, it is diatomic. So just to remind you of these, because this was back in like chapter 8, and it's been a while, okay? There are 7 elements that when they're by themselves, meaning they're not bonded with anything, they always exist with a 2 on them, okay? So there's Br. So there's the reason why I say Brinkelhoff. So there's B if we spell it out, BRIN CL H O and F. Okay, that's why I say Brinkelhoff. So if you spell out Brinkelhoff, those are all of the elements that when they're by themselves, they're not bonded with anything, they are diatomic. So oxygen is one of them. So when you have oxygen by itself, and it's not bonded to any other element, it's O2, not just O. And then this makes iron 3 oxide, which would have a chemical formula of Fe2O3. Okay. Now I'm not going to go into how do we write all the chemical formulas and stuff. That was back from chapter 9. If you don't remember how to write ionic chemical formulas, go back, watch those videos. It's going to be very important in this chapter that you know how to write chemical formulas. Okay. If you mess these up, it pretty much just messes everything up. So this would be an example of a chemical equation from this word equation where we've taken everything and we've written chemical formulas rather than names. All right, we're going to skip past these practice problems. I have a video of me going over those. If you want to watch that, you can go watch that. We're just going to keep talking about information. So how do you write a skeleton equation? All right, so first off, what is a skeleton equation? So this is very similar. This is exactly what we just did. We write the formulas of the reactants to the left. We have the yield or the arrow sign in the middle, and we have formulas of the products to the right. So this that I just wrote out here, this is a skeleton equation, okay? So this is a skeleton equation, and this one above is a word equation. Now you might be thinking, well, what's a skeleton equation? I thought this is just a chemical equation, right? What does that mean? So think of a chemical equation like a recipe. Okay, if you've ever followed a recipe before, like to make a cake or to make dinners, whatever, typically it doesn't just like tell you what you need. It tells you what you need and how much, right? So imagine that we had a recipe like make a cake, and it's like, yep, get some flour, get some eggs, some milk, some sugar, some vanilla, some cinnamon, and you put it all in a bowl and mix it together. You're probably going to go, well, how much flour? How much milk? How many eggs? How much sugar? How much vanilla? How much cinnamon, right? So this equation here, this might look like it's good. Like, well, I don't see what's wrong with this, right? Well, there's a problem, and the problem is it doesn't tell us how much. It doesn't tell us how much iron, how much oxygen, and how much of this can we make. Okay, now in a little bit here, we're going to get into what we call balanced equations, in which case that at that point you'll understand what I'm talking about and how this doesn't show us how much we need. Okay, but there are things that we need to put here to make this work. And right now, it's not, it doesn't give us amounts. Okay, usually we would have numbers in front of this. So just to give you an idea, so when it's balanced, which again we'll learn about here in about 2, 3, 5 minutes, it would look something more like this. Oh, yeah. Okay, so when it's balanced out, we're going to have these big numbers in front here. And these basically tell us the amounts that we need. We need 4 irons, 3 oxygens, and we make 2 of these. But as to how do we get those numbers, we'll talk about that in a little bit here. So, all right. So skeleton equation, and this was, again, the one that we just saw here on the previous slide that I gave you as an example, does not include the relative amounts of the reactants and products. So, again, we just talked about this. We're going to skip past this a little bit because I just laid this out. So, there's a little slide here on catalysts. We're not really going to do a whole lot with catalysts, but we'll bring it up here real quick. So, a catalyst is something that when you add it to a chemical reaction and it speeds up the reaction, but it doesn't actually take place in the reaction itself. Okay, a lot of reactions can be very slow, and you don't want to wait for them to happen on their own. So adding a catalyst can dramatically speed them up. Again, we're not going to really deal with catalysts at all. They don't partake in the chemical reaction. They're just kind of there. So just knowing about them is really pretty much all you need to know. There's really nothing else to it. So. Okay, this little table here is actually pretty important. It shows a bunch of like symbols and stuff that you typically see when you're writing chemical equations and what they mean. So this can be helpful to kind of keep track of and remember, especially as we get further into this chapter, because we're going to see a lot of these symbols. So plus signs are used to separate out things like reactants and products. The arrow or the yield sign separates out the reactants and the products. That's kind of like the dividing line between both sides of the reaction. If the reaction is reversible, so we're not really going to talk about reversible chemical reactions, but some reactions can go backwards, right? So if you've ever thought like, oh, chemical reaction is permanent, right? Like once you do a chemical change, you can't ever change it back. It's actually not true. There are plenty of reactions that actually can go backwards, but if we did have a reversible reaction, we have like a double arrow that points both directions. But we're not really going to get into reversible reactions, so I wouldn't worry too much. We are going to start learning about physical states. So if something's a solid, a liquid, a gas, or aqueous means it's dissolved in water. A lot of times we want to put physical states. It gives more detail and description, and it can be very helpful, especially when we start getting into some chemical reactions, to know what things are solids, liquids, gases, etc. So usually there's like little parentheses. You put S or L or G or AQ after the chemical formula. If there is heat in a reaction, so like, if you have to supply some amount of heat or whatever to get the reaction to go, usually that is indicated with a little triangle over the arrow, or heat is written over it. We'll learn about chemical reactions later in this chapter, but we'll learn about combustion reactions. Combustion is when you light something on fire and it goes, right? most of those reactions don't happen until you give heat, right? You give it energy, and then once the heat is given to the reaction or the reactants, then the reaction starts. So this is typically shown to say like you need to give heat to this to make the reaction go. And then the bottom one here is if we had a catalyst, you would write the element symbol of the element used as a catalyst above the arrow if you had one. But we're not really going to deal with catalysts, so I wouldn't worry too much about it. Okay, so let's take a look at our first example problem here. Let's delete this picture. And let's insert a text box so that we can do some typing as usual. So it says hydrochloric acid and solid sodium hydrogen carbonate are shown before being placed in the beaker to react. All right, we just erased the picture. The products formed are aqueous sodium chloride, water, and carbon dioxide gas. Write a skeleton equation for this chemical reaction. All right, so there's a lot of stuff going on here. So let's try to like break this down a little bit, okay? Let's try to figure out what are our reactants and what are our products. And let's maybe write a word equation first so that we can kind of organize everything before we worry about writing chemical formulas. So it says hydrochloric acid and solid sodium hydrogen carbonate are shown before being placed in the beaker to react. So our reactants are going to be hydrochloric acid and solid sodium hydrogen carbonate. Now the solid part is just telling you what physical state it is. We don't need to include that, so we're just going to write sodium hydrogen carbonate. Okay, so they're being placed in a beaker to react. So those are going to react, and it says the products formed are. Okay, so we're going to make some products. Products formed are aqueous sodium chloride. Aqueous means it's dissolved in water, but we don't need to include that in our thing because it's not part of the chemical name. It's just the physical state. So sodium chloride, water, and carbon dioxide gas. So carbon dioxide. Again, it's a gas. We don't need to include that in its name. It's not part of anything in particular. So all right, this is what we have. Let's see if we can make this a little bit wider so it fits on one line. Very close. Right? What if we make the font a little bit smaller? There we go. I want to fit it all in one line so it's easier to see. All right, so here's what we got. Okay, so here's our reactants on the left. Here's our products on the right. We need to write a skeleton equation. So that means we need to write the chemical formulas for all of these things. And then that would be it. We're not going to balance it. Okay, so hydrochloric acid. All right, so we need to go back to remembering how we write chemical formulas again. So hydrochloric acid, any acid starts with H, okay, and H is always going to be H+. And hydrochloric means that the ion in this case is going to be chloride. Okay, so remember, my ride has hydrolix. So HCl, I'm sorry, H plus bonded with Cl minus. Okay, that's hydrochloric acid. So this is going to be HCl. Positive 1 H, negative 1 Cl, 1 and 1, they bond together. So that's the first one. Sodium hydrogen carbonate. All right, so this one sounds confusing and scary, but we have sodium, which is Na. That makes a charge of +1. Hydrogen carbonate is a polyatomic ion. It is on the back of your periodic table. Okay, so if you have your periodic table on hand, it is on the back. However, it is called bicarbonate, not hydrogen carbonate, but it's the same thing. So does HCO3 has a charge of -1. Okay, so that is hydrogen carbonate. So when these two bond together, we have Na +1, HCO3 -1. Those are just bond 1 and 1. They just bond together because their charges already balance each other. Then we have sodium chloride. All right. So sodium is Na, charge of +1. Chloride is Cl, charge of -1. Those would bond together. NaCl. Then we have water. Most of us know that water is H2O, so I don't need to probably go into that one. And then lastly, we have carbon dioxide. That is a molecular compound. So we have carbon, which is C, and then dioxide. So oxide is oxygen, and di means we have 2 of them. Okay, so this here is our chemical formula. Okay, or this is our skeleton equation right here. This is our final answer. Okay, that's what we're looking for. So let's, I don't know how I highlight, maybe I just highlight this. Let's highlight it in blue, I guess. There we go. Okay, that's our final answer. That's what they're looking for. We have all of our products written, all of our reactants written, separated by arrows, plus signs, all that stuff, and we're good to go. All right. So again, I'm going to skip past these questions. If you want help on those, go watch that video. All right, so balancing chemical equations. So what are the steps in writing a balanced chemical equation? So first off, let's understand what is a balanced equation and why do we need it. So first, we're going to write a skeleton equation, which we just did in the previous problems. Okay. Then we're going to use these numbers called coefficients to balance the equations that obeys the law of conservation of mass. So what are they talking about here? All right, so let's go back to the previous example that we were dealing with before of this iron reacting with oxygen to make rust, okay? And this is going to make more sense. So let's take a look at this reaction. So if we were to use like molecules to represent these things, okay? We have one iron atom on the left-hand side of our reaction. And we have reacting with 2 oxygen atoms, right? So we have one iron here reacting with 2 oxygens here. And on the product side, after these things have reacted with each other, we now have 2 irons and we have 3 oxygens. Now, maybe for someone who, of course, doesn't know chemistry very well, you might go, well, I don't see what the problem is. Here's the problem. We started with 2 irons. We started with 1 iron. And on the product side, we have 2. Where did the second iron come from? Now, the law of conservation of mass, as most of you probably heard before, says matter cannot be created or destroyed in a chemical reaction, right? You can't make matter out of thin air, and you also can't just erase matter either, just like delete it from existence. So where did this extra iron atom come from? We only had 1 to begin with. How do we have 2? We can't just make another one magically out of nothing. As well as we started with 2 oxygens, and over here we have 3. Again, we have an extra oxygen here. Where did it come from? It could have just like popped into existence, and we didn't like turn iron into our oxygen into iron, right? That would be alchemy, and that doesn't work either, right? We already learned way back earlier in this course that you can't turn one element into another element in a chemical reaction, right? John Dalton came up with that. So clearly there's something going on here that is not right. And the issue is the numbers of how many irons we have and how many oxygens. With the way we've written it, it looks like we have 1 iron reacting with 2 oxygens, and we make this 2 iron, 3 oxygen compound. That's not the ratio. That's actually not how it works. We actually are missing some numbers, okay? So this skeleton equation is like a recipe that someone has written, and they forgot to tell you how much of each thing that you have. So it looks like it's normal, but it's actually not, okay? So we need to balance this. And to balance it, we need to have the same number of things on each side of the reaction. So to do that, we are going to use coefficients, which are these big numbers that we put in front of things in a reaction to then tell us how many of each one we have, right? So if we made a list on the left-hand side of how many things we had 1 iron and 2 oxygens. And on the right, we have 2 irons and 3 oxygens, okay? So we need the same number of irons and the same number of oxygens on both sides. So to fix this, let's just write this down below here real quick so we can do it on this one. So to fix this, we need to have 2 irons on the left. So if we put a big 2 in front like this, okay, and we'll do it down here down below. If we put a big 2 in front of the irons, that gives us 2 irons. Because it's going to multiply. 2 times 1 iron, that gives us 2 irons. That bounces out with the 2 on the right. Okay? As for the oxygens, we have 3 on the right and only 2 on the left. So those are not the same. So if we put a 2 in front of this will multiply the oxygens to give us 6. And that is a number that 2 on the left can multiply into as well. So if we put a 3 in front of this oxygen, that will multiply those oxygens to also be 6. Okay. Now this changes our number of irons. Here we originally only had 2, but now that we put a 2 there, that gives us 4. On the left-hand side, we had a 2, and, oh, sorry, I should put it there, I guess. On the left-hand side, we had only 2, but now we need to change that to a 4. Okay, so if we do this, we'll see that we have 4 irons here and 4 irons here. Those are the same. We have 3 oxygens here. I'm sorry, we have 6 oxygens here, and 2 times 3 gives us 6 oxygens there. And now we have the same number of atoms on both sides. Okay, so before we were looking at a reaction that looked like this, that basically looked like this bottom one, where it looked like it's like, okay, we have 1 iron reacting with 2 oxygens to make this, one thing. That's actually not true. It's more like we have 4 irons reacting with 6 oxygens to make 2 of these compounds in the end. That's really what's happening. Okay, so this down here below is like your actual real recipe where it's telling you, yeah, well, you don't just take like some flour and some sugar and milk and you make a cake. You take 4 cups of flour and 3 cups of sugar, and that will make you 2 cakes. That's really what's going on. Okay, so this is what we call a balanced chemical equation. So here's just another example where we are using coefficients. Again, those are the numbers, these big numbers out in front of everything to show you how many of each thing you have. This is just a simple little thing here to show how you make a bicycle. You take 1 frame, 2 wheels, 1 handle, 2 pedals, and you make 1 product with a chemical formula that looks like this, and that would be 1 bicycle. Okay? So this is, again, a balanced chemical equation. These coefficients are these big numbers that we're putting in front of everything to show how many that we have. So notice the difference here between the subscripts, which are the little 2's written down below things, and the coefficients, which are the big 2's written in front of things. Okay? Small 2's, subscripts, are telling you that these are like together, like bonded together, right? There's 2 of them, they're bonded together. Whereas coefficients tell you that there are 2 separate things. Okay? So it's kind of like grammar. You got to understand the grammar. So this shows you an example of a chemical reaction that would be balanced. And this one actually just happens to be balanced on its own. But we have the same number of atoms on both sides. We have 1 carbon atom on the reactant side, 1 carbon atom on the product side. We have 2 oxygen atoms on the reactant side, 2 oxygen atoms on the product side. This would be balanced. And this is actually a chemical reaction that is already balanced completely on its own without having to do any coefficients. That sometimes that's just how it happens to work out. So not every chemical equation actually needs to be balanced. Some just automatically are balanced on their own, like this one. All right, so let's take a look at another example here. Okay, so we are going to write out the reaction between hydrogen and oxygen to form water. And they want us to write the balanced equation. All right, so let's start with the word equation. So we have hydrogen reacting with oxygen to form water. Okay, that's a word equation. Let's write the chemical formula. So we have H2. Okay, so H2 is a Brinkelhoff. Again, just to remind you, let's go back to the stuff at the beginning I had written out. And that is here. Okay, these are all the elements that when they are by themselves, they are diatomic. There needs to be a 2 on them. So when we write H and O by themselves, it's H2 and O2, not just H and O. So H2 plus O2 makes H2O. That's our skeleton equation. And we know it's a skeleton equation because if we count how many things we have on each side, we have 2 hydrogens here and 2 oxygens on the reactant side. On the product side, we have 2 hydrogens and 1 oxygen. So this is a skeleton equation because things are not balanced. Okay, so this is a word equation. This is a skeleton equation because things are not balanced. So our balanced equation, balanced equation needs to have coefficients in front of everything to make it properly balanced out. So balanced chemical equation, again, we're going to have H2 plus O2 to make H2O. And the only thing here that's not balanced is the oxygens. So we only have 1 oxygen on the right. We have 2 on the left. So let's put a 2 here. Okay. So if we redo our count down here, down below, let's just do this. Let's copy this and let's just paste it down here. Like this. Okay. So we put a 2 here. That gives us 2 oxygens. That also now changes our hydrogens from being 2 to being 4. So on the left-hand side, our oxygens are balanced, but our hydrogens are not balanced anymore. So in order to make this a 4, we're going to need to put a 2 there. That will change our 2 hydrogens to being 4 hydrogens, which will balance out with the ones on the right. The oxygens are still balanced, and so this is our balanced equation, and that's what they are looking for. Okay, that is our final answer. All right. So you'll notice that if you make a list of things on each side, it's easier to keep track of. And you can kind of go back and forth and back and forth. You'll notice that you'll balance one thing, which then might unbalance something else. You got to go rebalance that one. And you kind of go back and forth until everything works out. Okay. Sometimes can be annoying. The main thing also to understand is that these numbers need to be the smallest whole numbers that you can get. So what I mean by that is this. Let's say that we balance this out and it becomes 4H2 plus 2O2 and 4H2O. Okay, let's say that we did this. We can reduce all of these numbers, right? Like we could divide a 2 out from this, and from this. They can all be reduced down. And sometimes when you're balancing, you might actually miss the first numbers, and you might get it right, like at higher numbers. In which case, notice that if you can reduce the numbers, you have to simplify them down to the smallest whole numbers that you can get. So in this case, we could divide a 2 out from everything and divide this, 4 divided by 2 would give us 2. 2 divided by 2 would give us 1, which we don't write. And 4 divided by 2 would give us 2. It would reduce down. Okay. So the numbers that we have need to be the smallest whole numbers you can get. If you can reduce them down, reduce them down. In this case, though, we have 2, 1, 2. There's no common denominator that you can do from those without getting fractions. So that is all we can do. That's the best we got. That's our answer. Okay. All right. Take a look at another one here. So this one says aluminum is a good choice for outdoor furniture because it reacts with oxygen in the air to form a thin protective coating of aluminum oxide. Balance the equation. All right. So they just want us to balance it. We don't even need to write anything else out. So let's just write this down below. So Al plus O2 makes Al2O3. Let's make a list real quick of what we've got on each side. So we have 1 aluminum. Hold on 1 second here. All right, so we have 1 aluminum. We have 2 oxygens on the reactant side. Ooh. On the product side, we have 2 aluminums, and we have 3 oxygens. So we can see that the aluminums and the oxygens are not balanced. So to balance this out, let's balance the aluminums first. On the product side, we have 2. On the reactant side, we only have 1. So let's put a 2 there. Okay, that will give us 2 aluminums. Now that balances the aluminums, but it doesn't balance the oxygens. Okay, now we have 3 oxygens here and 2 there. We cannot multiply 2 by anything to make it a 3, or at least not a whole number. So instead, let's think of what is the first number that 2 and 3 both multiply into. That would be a 6. So if we put a 2 here, that will multiply the oxygens by 2. So instead of having 3, we'll have 6. That's also going to change our aluminums from being 2 to 4. We'll fix those later. Okay, let's balance the oxygens still first. So here we had 2 oxygens. We need to make it 6. Let's put a 3 there. That will then give us 6 oxygens. And so that balances the oxygens out. And then lastly, we got to balance the aluminums. So here we have 4. So let's change this 2 to being a 4, which will then give us 4 aluminums like that. And then everything is balanced out. Okay. So our balanced equation is going to be this one written here up above, which is 4 aluminums, 3 oxygens, and we make 2 of this product. Something like that. Okay. So this is what we're looking for right there. We'll delete that. All right. So there are just, I think, some more practice problems here. Again, I have a video of me going over these, so if you need help on those, go watch that video. But that is it for this section of notes. All right, guys, I will see you in chapter 11.2. Bye.